This lecture is about the Fibonacci heap, a rather advanced data structure which implements the priority queue. Indeed, it was invented specifically to speed up Dijkstra's algorithm, which makes heavy use of a priority queue. It makes very frequent use of the push and decrease key operations, so those need to be extremely fast, and it makes further use of popmin, so it needs to be moderately fast. We can approach the Fibonacci heap as just another data structure to learn, or much more interestingly, we can think of it as an attempt to solve a problem. The problem is, how do we make priority queue very fast? So let's first of all review the other implementations of priority queue that we've seen and ask what we can learn from them. Let's start with the very simple linked list implementation. This implementation had extremely fast push and decrease key. All that those operations did was they placed the new item, or they decreased the key of an item. They didn't maintain any structure at all in the rest of the list, and this meant that these two operations could be extremely fast. The downside, of course, is that popmin had to do lots of work. It's got nothing at all to help it find the next smallest item. Now let's look at a lesson that we learnt from the binary heap. It's not actually shown in this table, but it's an interesting feature of the binary heap. The interesting feature is that if you're trying to create a binary heap, you could do n push operations, which would cost O of n log n, or alternatively you could just place the n items in the array and then heapify them all in one go, and heapify on n elements costs only O of n. In other words, it's more efficient to do cleanup in batches when we really need it, rather than tidying up as we go. Question is there any way that we could modify the linked list so that when it does one batch of tidying up to find the next smallest element, some of that structure can be reused the next time it needs it? The next piece of insight that we can get is from thinking of the binomial heap and the fact that its push operation had O of 1 amortized cost. Let's just review why this is. In the binomial heap, most of the time, when you push a new item, all you need to do is touch a few small trees of degree 0, degree 1, degree 2. Most of the time, you don't need to touch any of the big trees of depth log n, and that's what allows it to be cost O of 1 amortized. And so the question here is there any way that we can achieve the same benefit for decrease key? Is it possible for us to make it so that when we do decrease key, all we need to do is touch a very small amount of the data structure? The Fibonacci heap is a data structure which achieves all of these modifications that we've described. The Fibonacci heap has cost O of log n for popmin, O of 1 for push, and O of 1 for decrease key. All of these where n is the number of items in the heap, and all of these costs are amortized. Let's just remind ourselves what we mean by amortized costs. For any sequence of operations consisting of n1 popmin, n2 push, and n3 decrease key operations, starting from empty, the aggregate true cost is less than or equal to the aggregate amortized cost. And here, the aggregate amortized cost of those three operations is just n1 O of log n plus n2 O of 1 plus n3 O of 1, which we can simplify to O of n1 log n plus n2 plus n3. Just a quick remark, n here is the number of items in the data structure. Obviously, if we start from empty, as we've said we do, n is less than or equal to n2. So this is the motivation for the Fibonacci heap. Let's now go ahead and look at how it's implemented. In a way, it's a blend of the binomial heap and the linked list. This is what a Fibonacci heap looks like. It consists of a list, and each list item is a tree. Furthermore, each tree in the list is a heap. Heap property, remember, a node's key is less than or equal to the keys of its children. And that makes it easy to figure out what's the smallest element in a tree. In this particular picture, the trees happen to be binomial trees, but that's not necessarily the case. The Fibonacci heap allows the trees to be any shape. Also, we'll keep track of the min root. We'll keep track of which of the trees has the smallest root, like we did in the linked list implementation. Okay, so that's what a Fibonacci heap looks like. Let's review what the operations on the Fibonacci heap are. First of all, we'll look at push. This is all that push is. When you push a new item, you just add it to the list of trees. A new tree consisting of just one node, we'll just stick it onto the list and leave it there. So just like the linked list implementation, we're being very lazy when it comes to push, and this will mean that push is very fast. If we push a new item, we'll just append it to the list. And when we push new items, we should also update the min root, of course, if necessary. Let's look at the next operation. Let's suppose we do pop min. When we pop min, we remove the min root, we remove the smallest item. As with the binomial heap, we now have some children. What do we do with them? We promote them to the root list. We'll take these children, 4 and 3, and we'll promote them to the root list. And then the rule for pop min additionally says, after you do a pop min, then go through a full process of merging trees. Exactly the same rule as we applied for the binomial heap. Will say if there are 2 trees of the same degree, in other words 2 trees whose root item has the same number of children, whenever there are 2 trees of the same degree, we'll merge them. So here, for example, 7 and 3 are both trees of degree 0, so I'll merge them. When I merge them, I have to make 3 the parent and 7 the child, because I want to maintain the heap property. Are we done yet? No, we're not done. I can see here 2 trees which have the same degree. These trees, the root element has degree 1, so we'll merge them in the normal binomial fashion. I'll make 4, 6 a child of 3. Are we done yet? No, we're still not done. We still have 2 trees which have equal degree 0, so I'll merge them, and now we're done. And finally, update the min root. We'll just scan through all of the trees that we've produced and ask which of the trees has the smallest root. So we have done a whole load of cleanup operations, and we have recovered a Fibonacci heap at the end of it. So, just to summarize what we've said here, the Fibonacci heap is a lazy data structure. It just dumps new nodes into the root list, and it doesn't do any tidying up until the next call to pop min. The reason why this is a good idea is the intuition we had on the previous slide, which says it's more efficient to do cleanup in batches rather than doing little bits of cleanup as you go. Let's look at a code snippet. The Fibonacci heap maintains a list of heaps. Each heap is a tree, and the way it stores that, it just stores a pointer to the root node of each of the heaps. In addition, it maintains a pointer pointing to which of those roots is the smallest. Whenever you push a new node, all we do is we create a new heap consisting of just a single node. We add that new heap to the list of roots, and if necessary, we update the min root pointer. When we do pop min, we're going to extract the root node that's pointed to by min root. We'll extract it, delete it from the Fibonacci heap, and we'll promote its children to be roots. Then we go through this cleanup procedure of repeatedly merging 2 roots with the same degree. And then at the end of it, once we've finished merging, we'll update min root and we'll return the old min root that we just extracted. Okay, now let's look at the next function that's important here, the decrease key function. This is the real challenge, because this is the function that the binomial heap was not able to speed up. Here's how decrease works. If we want to decrease a node, decrease the key of a node, and we decrease it, but we don't decrease it enough to violate the heap condition, here we're okay, 3 is still larger than 2, so we still maintain the heap property. If we maintain the heap property, then that's all we need to do. We don't need to change anything. That's straightforward. Incidentally, just a quick note, what do we mean by decrease key? As we did in the binomial heap, we'll imagine that there's some node object here. The node object will maintain the key of each node. It will maintain some sort of payload depending on what you're using the priority queue for. We'll keep track of the current degree, i.e. the number of children that each node has, and we'll keep a bunch of pointers around. And I'll imagine that when we call decrease key, I'll imagine that V is a pointer towards a full node object. So in other words, when I call decrease key on a node, I'm going to assume that I know what that node's parents and children and siblings are. Okay, let's see what happens if we decrease key again to a smaller value. If I take that node 3 and I decrease its key even further to 0, this is no good. I'm violating the heap condition. I'm not allowed to have a smaller node as the child of a larger node. So I have to do something. In the binomial heap, our solution was bubble up that smaller node to the top of the tree. We're going to use a different solution here. We're going to be lazy. We're going to be inspired by the linked list implementation. We'll just splice it out of the tree and dump it into the root list. And we know that popmin will come along sooner or later. Popmin, next time it's run, will do the cleanup operation. So what we're going to do, we'll just dump any heap violating nodes into the root list to be cleaned up by the next popmin. Our argument for this, remember, is that it's more efficient to do a whole load of cleanup in one go rather than small incremental amounts of tidying up. There is, however, a problem with this that's quite easy to see. You can imagine doing decrease key repeatedly on all of the grandchildren, ending up in the situation where we have a small number of trees, each tree with a very large number of children, but hardly any grandchildren. In other words, we might end up in a heap where the trees have big omega of n children, and so that means that next time we call popmin, we might end up having to pay big omega of n to promote all of those children. So in other words, we would end up with extremely slow popmin. We'd end up no better than the linked list situation. The Fibonacci heap needs something to avoid this. We can't allow this state of affairs to develop. So that's the real genius behind the Fibonacci heap design. Here's the trick. It uses a pair of rules. Lose one child and you are marked as a loser. Lose two children and you are dumped into the root list. In this particular case, the node 2 lost one of its children, so it was marked as a loser. The inspiration behind this is we said we want to avoid the situation where you have a grandparent, large number of children, hardly any grandchildren. So let's play this out. Let's imagine we take that node 7 and we decrease key, decrease it down to 1. This is now a heap violation, so we're going to be lazy. We'll just cut out the 1, we'll place it into the root list. Now the node 2, previously it was marked as a loser, now it has lost another child, it's lost 2 children, so we'll apply the disowning rule, we'll dump the node 2 into the root list. And we end up with this Fibonacci heap. Let's see how this rule plays out in another situation. It's just nice to see another example. Here's a node 9. I'm going to apply decrease key on this node to 6. This is now a heap violation, so I have to splice out the 6 and I'll move it to the root. 8 had previously been marked as a loser. Now it's a double loser, so I'm going to dump it into the root list. Incidentally, when we dump stuff into the root list, we'll remove its mark. We'll see why this is appropriate when it comes to analysing the amortized cost of this. Okay, so let's review. The node 5, previously it had been marked as a loser. It lost one of its children, so it's a double loser. So we apply this disowning rule. The 5 gets dumped into the root list. And at the end of it, 4 lost one of its children, so we'll mark 4 as a loser. So just to repeat, Fibonacci heap nodes have a brutal mechanism to make sure they have enough grandchildren. If your children don't have enough children of their own, then you disown your children. This rule for decrease key, this business of marking nodes as losers and dumping them into the root list, it's an extremely clever design, and to really appreciate the cleverness of the design, we'll have to wait until we do the full amortized analysis of complexity. Let's review the code behind the decrease key operation. Firstly, we've said each node is going to store a flag, keeping track of whether that node has been marked as a loser or not. When we decrease the key on a node, we first of all ask ourselves, is there any violation of the heap condition? If we don't violate the heap condition, we don't need to do anything at all. If we do violate the heap condition, then we walk up the list of parents, and at each parent, we take its child away, put the child into the list of roots and mark it as no longer a loser. That's just elements in the root list. The rule is they are not losers. And we keep on walking up the parent list until we reach a node which is not a loser. Remember, at this stage we have spliced out all of its children and dumped them into the root list, and we've come finally to a parent which is marked as not a loser, so we mark it as a loser, and then we're done. When we popmin, there's just a minor modification to the popmin rule. We do basically the same as we did in the simple version described before, but with the minor modification that we are going to insist that all nodes in the root list are not losers, so first of all we'll mark all the min roots children as loser equals false before doing the merge operation. There's an awful lot of very finely balanced conditions in this algorithm which are sort of hidden. It's very easy to look at the source code and not appreciate the subtlety. When we go on to do the amortized complexity of analysis, that's when you'll really begin to appreciate the subtlety of how all of these rules play together. Let's also look at a little code snippet just to expand on the rules behind the cleanup operation involved in popmin. Here's the code behind the cleanup procedure, the procedure for merging trees. Let's run through an example. Let's imagine we have this list of roots. The algorithm for cleanup, or one way to implement cleanup, is to iterate through each of the roots. First of all, I'll look at this tree, the tree with key 7. I'm going to maintain an array, the root array, and this root array will have one slot for each degree. So I take my 7 and I place it into root array entry 0 because this is the place where I put trees of degree 0. I look at this, the next tree in my list. This tree has degree 1, so I'll just dump it into the root array. I'll place it into root array slot 1. Next, I'm looking at the next tree in my list of trees. This tree has degree 0. Hold on, I can't put it into root array slot 0 because there's already something there. I'll take that 7 and I'll merge it with the 3. So now I have a tree of degree 1. I ask myself, can I place this tree into the root array? No, I can't because there's already something in that slot. So I'll take the existing thing and the thing I want to put in there and I'll merge them. And now I can put this into the root array because there's nothing in the root array yet of degree 2. Let's keep on going. Next node to look at is 5. This has degree 0. That slot is empty, so I can place it into the root array. Next I'll look at 8. Same problem as before. Slot 0 is got an occupant already, so I have to merge those two. This time round, I'm going to merge them to put the I'll put the 8 on the bottom, the 5 on top. Whenever I merge two trees, I'm trying to maintain the heap property, so I put the smaller element on top. Okay, so now this is safe to put into the root array. I'll just put it in here, element 1. And finally, at the end, I'll take all those trees and return just a list of the trees. Remember, the Fibonacci heap, it maintains a list of roots. So this is the operation for merging trees, very straightforward. So let's just recap. The Fibonacci heap uses two principles. Principle number 1, sometimes it pays to let mess build up, because it can be sometimes more efficient to do cleanup in batches rather than small bits of tidying up as you go along. Second rule is that your parents want lots of grandchildren, and they achieve this quite straightforwardly. If you don't have enough children, then your parents will disown you.